I'm William Luxford. Welcome to Module 1, History and Basic Principles of Cochlear Implantation. Although the first attempt to electronically stimulate the auditory system occurred over 2 centuries ago, the development of a cochlear prosthesis to restore hearing to patients with sensorineural hearing loss happened only over the last half of the 20th century and has continued into the 21st century. In the 21st century, the Lasker DeBakey Medical Research Award in 2013 honored 3 individuals, Graham Clark, Ingeborg Hochmeyer, and Blake Wilson, for their work in creating, manufacturing, and studying the modern cochlear implant, a device that has tremendously enhanced the lives of implant recipients, both adults and children, and their families. These 3 individuals, Graham as the clinician, Inga and her husband Erwin as a manufacturer, and Blake as a scientist, are representatives of the many people that have worked or are presently working in the cochlear implant field. The Lasker Award encourages clinicians, manufacturers, and scientists to continue to improve the cochlear implant so that one day in this century or the next, truly normal hearing can be restored to patients with sensorineural hearing loss. Electrical stimulation of the auditory system began centuries ago. Volta is credited with the first attempt to electrically stimulate the auditory system when in 1790 he inserted metal rods into each ear. Upon closing the circuit of approximately 50 volts, he described the response like a blow to the head, followed by the sound of boiling liquid. This very unpleasant experience probably discouraged other researchers interested in electrical stimulation of the ears. Years later, in 1930, Weaver and Bray discovered an electrical potential which arises in the ear as a result of acoustic stimulation. This discovery, clarified by other researchers as the cochlear microphonic, gave rise to the concept that the ear acted like a transducer of acoustical to electrical energy, creating enthusiasm for the possibility of artificial hearing through direct electrical stimulation of the cochlear nerve. The first report of stimulation of the acoustic nerve by direct application of an electrode in a totally deaf person was in 1957 by Dejourno and Ayres in France. A 50-year-old man previously operated upon for cholesteatoma was being reoperated for the repair of a facial nerve paralysis. During the second surgery, an active lead was placed on a segment of the auditory nerve visible through the vestibule and an indifferent electrode implanted in the temporalis muscle. With stimulation, the patient reported hearing sounds like crickets. The increased awareness of the speech rhythm helped his speech reading ability. He did not have speech discrimination. The optimistic view of the potential benefits of electrical stimulation of the inner ear, as detailed in newspaper accounts of the work of Dejourno and Ayres, was dampened by the considerable doubt about the safety of inserting anything into the inner ear. However, the possibility of developing a safe cochlear implant accelerated in the late 1950s with the evolution and developments of microsurgical techniques, stapes surgery, and the facial recess approach to the middle ear. Electrical stimulation as treatment for profound sensorineural hearing loss would become a reality in the following decades. Working independently, William House, Blair Simmons, and Robin Michelson began their work on cochlear implants in the 1960s. The newspaper reports of Dejourno and Ayres' work brought by a patient to William House stimulated his investigation into the effects of electrical stimulation on the inner ear in 1960-61. He studied the electrical stimulation of several patients undergoing stapes surgery. From his experience and that of others studying the electrode and tissue tolerance related to thermal, chemical, and electrolytic factors in animals, it was felt that a profoundly hearing-impaired person could be implanted with reasonable safety. In 1961, William House in Los Angeles implanted 2 profoundly hearing-impaired patients with a single hardwired gold electrode placed in the scala tympani. Both patients perceived a sensation of hearing with electrical stimulation. However, because of infection, the wire was soon removed from the second patient, and in an attempt to obtain better loudness tolerance, the first patient was soon changed to a 5-wire electrode induction coil system. The electrodes were implanted through a mastoid facial recess approach to the round window and into the scala tympani. The electrodes were insulated with silicone rubber. The device was rejected 2 weeks after implantation. In 1964, Blair Simmons at Stanford University in Palo Alto reported extensively on the direct electrical stimulation of the auditory nerve of a deaf man who was implanted with a hardwire cluster of 6 stainless steel electrodes into the auditory nerve through the mandibulus. After the several-month study, the electrodes were removed. In 1968, Robin Michelson at University of California, San Francisco, working with cats, found that intercochlear electrodes could function and were tolerated safely for long periods in the experimental animals. During the 1960s, as in the 1950s, there were other developments that aided the progress of cochlear implants. Advances in cardiac pacemakers increased the knowledge of biocompatible materials, insulation of electrodes, and effects of electrical stimulation. The developments in electronics as a spin-off of the space industry allowed for better and smaller circuit designs. The cochlear implant gained notoriety in the 70s with print, radio, and television publicity. Significant advances were made in the United States, Australia, Austria, and France, working with a select group of deaf patients with realistic expectations who did consent to participate in the implant projects. Information from the early work of the California investigators was presented at the American Otological Society meetings in 1971 and 73. The first international conference on electrical stimulation of the acoustic nerve as a treatment for profound sensorineural deafness in man was held in San Francisco in 1973. At the 1971 American Otological Society meeting, Robin Michelson presented his work on 5 patients implanted in 1970 to 71. 2 of the patients heard only noise and therefore were dropped from the study. The remaining patients were studied extensively by the UCSF team over the next 2 years, and their data, along with an animal data on cochlear implantation of cats, was presented at the 1973 Otological Society meeting. At the same 1973 meeting, William House, working with Jack Urban, an electrical engineer, reported on 3 deaf patients that had been implanted in 1969 and 1970 using a multiple electrode device. 1 patient developed an infection of the percutaneous button after a few months requiring device removal. They used multiple electrodes in an attempt to achieve both periodicity and place pitch and a hardwire system to have better control of signal input. After many variations of the stimulating signal, especially with 1 patient, they found that the best input was a simple circuit using a 16 kilohertz carrier wave amplitude modulated by the electric analog of sound. Therefore, a single-wired induction system was constructed and implanted in the patient's other ear. This was the first patient to use electrical stimulation of the cochlea outside of the laboratory on a consistent basis. At the time of the 1973 meeting, the patient had used a wearable take-home stimulator for approximately 1 year. The patient felt that the implant helped with his awareness of environmental sounds and lip reading, though he could not understand speech. Since the patient maintained similar electrical thresholds over the year, House felt that there was no evidence the electrical stimulation within the cochlea had caused further degeneration of the remaining neural elements. Though William House had begun work on multi-channel implants, his group concentrated its efforts on single-channel devices. In 1976, a team at Eye, Ear, and Hospital in Pittsburgh, sponsored by a grant from the National Institutes of Health, performed an independent evaluation of 13 single-channel patients, 11 implanted by Dr. William House and 2 implanted by Dr. Robin Michelson. The Pittsburgh group found that the patients could detect environmental sounds, had improved speech reading, but could not develop speech discrimination. Encouraged by the positive patient responses, William House invited 6 other physician groups to participate in the study of single-channel implants in adults. Graham Clark, who began studying the effects of electrical stimulation of the auditory nerve in animals in 1969, did extensive work in the 1970s developing a multi-channel cochlear implant. 3 patients were implanted in 1978 and 79. All initially noted that the perceived pitch varied according to the rate and site of stimulation. A device failure occurred in 1 patient soon after implantation. The test results from the other 2 patients helped him develop a speech coding strategy. Ingeborg and Erwin Hochmeyer of the Electrical Engineering Department of the Technical University of Vienna, with Kurt Burian as their otologic surgeon, implanted 5 patients during the 1970s with multi-channel devices. They found that stimulation of 1 single channel of a multi-channel intracochlear electrode array using a simple correlate of the analog of speech signal did result in some useful speech understanding. Claude Henry Chouard began his work in the early 1970s. Infection around the percutaneous plugs required removal of all the implanted devices in his early patients. In the late 1970s, he changed to a transcutaneous design, and several patients were implanted with this multi-channel system. The signal processor was carried in the shoulder bag. In the 1970s, cochlear implantation was not readily accepted by the scientific community. Safety and efficacy were the primary concerns. The patients were the greatest champions of the implant, urging the early investigators to continue their work. By 1981, approximately 200 patients worldwide had received cochlear implants. Medical device manufacturers providing reliable production and maintenance facilities sponsored clinical trials under governmental control that showed cochlear implants were safe and provided benefit to the profoundly hearing impaired patients. The question changed from should anyone receive a cochlear implant to who should receive an implant and what benefits should the recipient expect. House and his co-investigators, after seeing the benefit the cochlear implant provided adults, began implanting children. The House group teamed with the 3M company, developing the first cochlear implant to receive Food and Drug Administration approval in 1984. Graham Clark, working with Nucleus Limited of Australia, which formed the Cochlear Corporation, helped the company design and fabricate a wearable multi-channel cochlear implant. The work begun by Michelson at the University of California, San Francisco continued through the efforts of Michael Merzenich, Robert Schindler, and Minimed. Their work was incorporated into the founding of the Advanced Bionics Corporation, AB, in 1993. Devices designed by AB received FDA approval for adults in 1996 and for children in 1997. Ingeborg and Erwin Hochmeyer formed the Medical Electronics Corporation, MED-EL, in 1986. The MED-EL implant received approval for implantation in Europe in 1994 and FDA approval in 2001. In the early 1980s, there were many centers in many countries investigating the cochlear implant. Over the following years, many of them either stopped their work or their work was folded into another group. 3 companies with worldwide cochlear implant experience led the way into the 21st century: AB, Cochlear, and MED-EL. In the 21st century, cochlear implant manufacturers are incorporating improvements in microphone technology, digital signal processing, and wireless communication accessories that have occurred in the hearing aid industry into their implants. In 2009, Advanced Bionics was purchased by Sonova, the owner of the hearing aid manufacturer Phonak. Cochlear Corporation is working with Resound, a hearing aid company. The implant team of physician, engineer, and patient of the 1970s expanded in the 80s and 90s to include audiologists, speech and language therapists, educators, scientists, and others, all working with the improved technology and signal processing to enhance the benefits the implant patients received. The improved benefit, especially for the young child, allowed the FDA to lower the age of implantation to 18 months in 1998 and 12 months in 2000. Initially, there was some significant criticism in the deaf community regarding implantation of children. Though the criticism continues today, the improved benefit to children has markedly decreased the initial uproar. In the early 80s, the basic elements of cochlear implant consisted of 1. A microphone to pick up the sound and send the auditory input, 2. The signal processor, which transforms the input into an electrical signal that was sent by an external transmitter, which sends both power and information to an internal receiver, which decoded the information and transmitted the signal through electrodes into the scala tympani of the cochlea. All implant companies have made improvements in the basic elements over the years. Probably the most appreciated change was the movement of the wearable signal processor from the body to behind the ear. Implant candidacy indications have changed. Patients with more residual hearing are candidates who require changes in electrode manufacturing and the surgical approaches to preserve the residual hearing. All implant manufacturers strive to create smaller, safer, and reliable cochlear implants that restore hearing. Though the hearing restored by the present device is very beneficial, it is not normal hearing. That is the goal. Thank you for viewing this module. We look forward to seeing you next week.